fairly quickly. Most of you had it, most of you did quite nicely on it, so wasn't too difficult, I don't think. First problem asks about the highest pressure point on the plug. So you had to find the deepest spot. Pressure, pressure, pressure. Some folks did hydrostatic force. Didn't ask for that, so did some extra work. 15 feet deep, right? And we're going to take the depth times the weight of the fluid, a specific weight. So 937.05 pounds per square foot is what I got. So just be careful to read these things. Like it could have asked for it in PSI, could have asked for it in PSF. It didn't on this one, but just note those kind of things when you read through. If you have questions, stop me as we go through. So the second one says, what's the hydrostatic force? When it says force, we're looking for pounds. That's what we're looking for out the end. So to get hydrostatic force, you got to draw the pressure curve. This is the pressure curve with the greatest pressure down here and the least pressure here. That's right, I changed this, didn't I? I said 9-foot wall, not plug. This is my original copy. So, and it was 1 foot deep on this little wall piece. So that's this piece right here. Coffee? Oh, coffee down. That's not good. It's all right. There's a roll somewhere, probably in the back room. Bummer. Sorry. I hate that when I lose my coffee. It's concrete floor. All right. Didn't hurt anything. All right. So you find your pressure curve. So I got 562 at the bottom of that one. It's up to 0. It makes a triangle. So the area of the triangle is half base times the height, and then times the distance in feet to get the volume. So area times its length will give you volume. And I think when I initially calculated it, I also forgot to apply the half. Got that number and then corrected it to that. So 2530 is the right number. The location is 2/3 from here. So 2/3 the height from the pointy end of the triangle, or 1/3 from the 90 of the triangle.
Is that where it's equal?
Yeah, that's just its balance point. So like, if you were going to do statics and you needed to concentrate that distribution, that's how you do it.
That's where the centroid is.
Yep. Yep. We're going through the exams and they're over there in a pile. So you got to get it yourself because you're late. Good morning, by the way. All right. Keeping on, keeping on. Object is placed vertically in the water. Has a cross section of 6 by 4, 24 inches long and weighs 30 pounds. Does the oh shoot. Picked it again. Kick it again. Perfect. Works pretty well. It's like a foot button. Determine if it floats or sinks. So a couple different ways you can go about this. You can do the displacement method, which means take the total volume of the object, right? And figure out how much water that is and how much weight that is. And if that water weight is more than the object weight, then it's going to float at some float line. If the object weight is more than the water displaced weight, then that thing's sinking. So that's kind of the first thing to do, is to go through that and determine if it sinks or floats. Hopefully you didn't make any mistakes on that one and determined it sinks. So then you didn't have to do a water line. Some of you did a water line anyway, which I thought was super interesting. I'm like, does that actually, that couldn't work. Like, yeah, somebody said like it would, the water line's like 4 feet underwater or something. I'm like, wait, I don't think that's classified a water line then. That's a sinking object. Anyway, I don't actually know what that evaluation is, but if it,
34 inches.
yeah, so I don't get that, because it's only 24 inches.
I did it. I didn't read that.
There's like no way. It would just keep going. There's no water line. Yeah. It's gonna go to the bottom of the ocean where sinking boats go. All right.
Sorry on that, if the object doesn't have enough weight and the deeper it goes, the buoyant force will make it to float, right, and away under the water.
Once it sinks, then it'll continue to sink. And actually, it speeds up. Because of the pressures, they're not exactly linear as you go down. So if you've done, like, scuba divers know this, but if you've done any actually deep diving, like without scuba gear, the deeper you get, the easier it is to stay down there. So the forces are not like linear as you go down. You have to recalculate. They're close though, close enough. All right, this one said determine the specific weight of the fluid. So I just gave you the volume of the fluid and its weight, right? 1,200 pounds in fluid weight. So really all you had to do is calculate a volume, divide by the weight. I think most of us did this one just fine. 21.22 pounds per foot cubed. And then this one, we're given a fluid and a specific weight. We're given some elevations and asked about pressure at P0, P1, and P2. The pressure at P0, it's gauge pressure, it's called gauge pressure, and that is 0. Now it has there's pressure on us right now from the atmosphere, right? So that's called atmospheric pressure. It's about 14 PSI. But gauge pressure just zeroes out when there's no pressure other than atmospheric pressure. So that's what I was looking for, was 0. At the top of a reservoir, we have 0 pressure. As we go down in depth, then we increase the pressure. And again, it was just a pressure calculation. So you did have to get the units in PSI. So it's 10.80 and it's 118.80 and 0 for P1 or P0. P0 was 0. P1, 10.80. P2, 118.80. Boom. We'll do it all again in exam 2. And then we'll add Bernoulli's equation to it, which we're going to start on today. So, Coolio. Questions, comments, concerns, political views? No, let's not do that. Let's not do that.
I didn't see the answer on question 2.
On question what?
2.
That's because you spilled your coffee.
Yes, I did. I gave it up already on it.
I know, now you got to get new coffee. The answer is 2530. Pounds, and that's right here. That's the concentrated distributed load, right? In the geometric center of the distribution, whatever the distribution looks like. So if it's a horizontal surface, that's a rectangular distribution, it's just halfway. Like if the plug or the gate valve is at the bottom of the pool or the bottom of the reservoir, right? All right. A lot of access ports are at the bottom of tanks. So if you have big tanks, a lot of times there's actually man doors down at the bottom of that tank. So when it's empty, you can get in and clean it out. So that's a perfect calculation for hydrostatic force. Like, how beefy do we need to make this man door, right? And the hinges and the stops and everything.
Can I ask you a kind of basic question real quick?
Sure.
So I'm struggling with the unit conversions.
Okay,
And I was under the impression that in order for unit to cancel, one had to be in the numerator and one had to be in the denominator.
correct.
That is correct,
That is correct.
Okay.
Absolutely correct.
because I wrote this down. I got the correct answer, but my units are in the numerator, all of them. And
So
they
if,
cancel out so I can get pounds for number two.
for this one,
Yeah.
yeah. So
Oh, wait, no, that feet, okay.
it's feet squared,
Uh-huh.
right? And then these 2 feet.
Yeah, so
So
the p squared is in the denominator.
Yeah.
So it's the way that I wrote it.
it probably is, it like,
Because I do have pounds.
the
per
right
foot
way to
squared.
write this would be like this, right? 9 feet over 1,
Right.
1 feet over 1. And that's a little more clear that the feet is above and this feet squared is below.
Okay,
So,
so
Yeah.
it's just the way I wrote it.
and then remember, when you have a fraction in the denominator down,
Uh-huh.
fraction down below, the denominator inside of a denominator flips up and becomes above.
Yeah, so if I had,
So if you do-
like pound per foot.
Yeah, this will happen
In the
in
denominator.
Bernoulli's a lot, because we're gonna have like velocity in the denominator. Well, that's feet per second. In the denominator, the second flips up to the top.
Okay,
Yeah.
Okay.
So it gets tricky. All right, very good. Good scores. Nice job. Homework. Let's go over that. So if you got your homework out, you need a different color device to write on it, or just don't write on it. You're supposed to have your homework done before. Gosh, dang it.
You did it again.
At some point, it's not gonna work when I kick it again, but it seems to be pretty consistent. So. First one was a 24-inch pipe. Velocity in the pipe was 6.21. Is that correct?
Yeah.
Feet per second. So then you should have just went and said 6.21 feet per second. Times the diameter of, what'd you do with the 24 inches? Put it in feet, 2 feet. Right? And all that's over the viscosity. And what's the viscosity?
1 times 10 to the negative 5.
And then what's the unit of that?
Feet squared, feet per second squared.
Feet per second squared?
Yeah,
Feet.
that.
Yeah.
squared per second.
That's what I thought. Feet squared per second. So there's a perfect example of the denominator in the denominator, right? So that means this second flips up and is up here. This second is down, so they cross. And we want that to cross, right? We want all units to cross. And then we have feet times feet and feet squared. So everything goes away. What'd you get?
1,242,000.
How much?
1,242,000.
242,000.
It's very turbulent.
Yeah, extremely turbulent.
I thought I had to double check. I thought wrong. It's like that's super.
So 24-inch pipe. 6.21 feet for every second. So 1,001, it travels the length of this table, 1,001, right? It's booking. And it's a lot. Like the flow rate would be huge. All right, good. Very turbulent. How about this second one? What'd you get for a Reynolds number? What's CFS?
Cubic feet per second.
Yeah, cubic feet per second. Yep. All right. What'd you get for Reynolds number?
91,671.7.
Anyone else get that?
73.25.
Oh, boy, we better do it.
I got it. I got 91,006.
Oh,
641.6.
2 votes for that. All right, let's do it. So diameter is 2.5 inches, correct?
Yeah.
Do you want to switch that to feet? All right, so I'm just gonna write it all out, 12 inches per foot. All right, so that gets multiplied. So I took the 2.5 inches 12 inches per foot, those cross. So that's good. What's our velocity? Is that our velocity? No. How do we get velocity?
Over A.
Yeah, so Q, the flow rate, equals A times V. Area times velocity, right? So velocity equals Q divided by A. Everyone okay with that so far? All right, so velocity equals, what's our Q? 0.15 feet cubed per second. You want to leave it in feet cubed and then we'll convert the area? Yeah, that's probably a good idea. So you can either convert the 2.5 right away to feet. That's probably what I'd do. 2.5, enter 12, divide. What is that? 0.2083333. Okay. So I'm taking the Q and dividing by the area. So I'm going to use pi d, which is the 2.5, which is 0.208.20833 squared over 4. Pi d squared over 4 is an area of a circle. And you can just use the diameter directly. So now you just got to figure out how to run that equation in your calculator. It's a lot of brackets if you're going to do it all at once. So you might just break it up. But it's really that number, right? Because now this is feet squared, correct? And it's going to kill 2 of those. So we're going to be left with feet per second. All right, what do you get for a velocity? Anybody have a velocity number?
4.3988.
Okay. Anybody else get 4.3988?
Yeah, 4.40025. I got 4.4017. Yeah,
I got 4.400316.
I think it's decimal. I did all the decimals.
I get 4.400333.
How about 4?
It's close enough.
All right, I'm running out of room, so I'm going to erase this one. My next problem. All right, so I get velocity, which is what you get, sounds like for most of you, 4.4, couple zeros, and I get 3. I'll just leave it right there. And the unit, feet per second. So we need that because that's in the Reynolds equation, right? We need the velocity. So that's going to go here. I'll just put V times V, right? And then I divide by, again, it's water, so it's 1 times 10 to the minus 5 feet squared per second. So with feet per second here, right, feet there, it should be good. Because the feet squared cross out and the seconds cross out. All right, now Reynolds number. So we get I get 91,000. Anyone else get that number?
91,673.
Yep. 91,673. What do you think? Turbulent? Laminar?
Yeah.
Yeah, turbulent by a factor of 9, right? Because 10,000 was our high, kind of our limit. All right, 91,673. Number 3. Now I don't have any details. What were we given?
4 inches.
4 inches.
And the discharge is 4.0.
4 inches in diameter?
Yep.
And we have a Q or a velocity?
Here.
Q. Flow rate, what is it?
4 times 10 to the negative third.
Say again?
4 times 10 to the negative third.
Oh, I remember that. What a weird unit.
CQ.
CFS? So feet cubed per second. So these are the things that typically you can measure. That's why we're given this data. Like, we can usually measure flow rate with a flow meter. And you can do that in closed systems, like they'll put them into closed systems, a flow meter. So you can literally just walk up to a closed system, a pipe, and read a flow meter of what's going through it, right? And then obviously you know the size of the pipe or you can measure it. So these are like analysis type problems where we're given things, we're given the system, and then we just learn, right, whether it's turbulent or not. You can reverse things and say, hey, here's the system, it's turbulent, we would like to make it laminar by changing the diameter of the pipe or by changing the velocity of the fluid, right? Or by changing the flow rate. How much do we need to change it? That would be more of a design type problem. All right. So you had to get a velocity, correct? What'd you get?
I got the 0.045837. 45837.
Anyone else get that for the velocity? What's that,
Yeah.
feet per second?
Feet per second, yes.
Very good. And that gave us a Reynolds number, pretty slow, right?
Yep.
Like 0.04? How many inches is that? Is that even an inch? It's not, it's a half inch. So it's going this far in a second, 1001. Like, that's a pretty, that's like a stream flow kind of thing. In a 4-inch diameter, yeah. What's your guess? Is it a laminar or turbulent?
Or laminar.
Yeah, definitely gonna be laminar. What's your Reynolds number?
1,546.67.
1,000.
Got one.
Yeah, see, when you say the thousands and stuff, I just can't process it. So it's 1526.67.
26.67.
There we go.
I got, because I used all the whole digit, 6 digits in my calculator.
I cut off the last,
1527.
I cut off the last two.
That's fine. It's definitely, for Reynolds number, it's just a feel, right? It's not a super accurate decision-making process as far as the decimal points of the number. Often you just see it in whole numbers, not even decimal points, so. Clearly under 2000 though, so that should be a laminar flow. Nice and smooth. All right, very good. Let's turn them in and your write-ups.
One line, right?
I don't have that right.
Write-ups need to come in online then, but the homeworks, if you have them, you can put them right here.
I left mine at home. Good night.
Oh my God, damn it. You're fired. You're fired.
That's great. You're organized.
Did
a really good job.
Yeah. Yeah, stapler's right there.
Can we turn the lab right up in person too?
Sure, absolutely. Same pile, yes, pile it up. I'll be able to clearly see. Perfect.
Yeah, we're supposed to do.
I've been waiting to tune in since the Monday before.
I know.
That Wednesday.
I know, girl.
Same.
Yep, pile it up. I got nothing else to do in my life other than look at your stuff. Job fair today. For those of you that weren't here in the beginning, job fair. 11 to 2, you should walk through and talk to people. Microchip's gonna be there, Benchmade's gonna be there. There was one other, there's like 30 of them, but some of them are not that interesting to me. But there was like 4 that were kind of interesting. Hmm? On the pile, man. In on the pile. All right, let's talk about energy and work And then we can work into Bernoulli's equation and fluid systems. But I don't think they talk about the energy part of it and the work part of it enough up front. They just head off into potential energy and kinetic energy and friction losses and pressure head, right? It's like, why are they just talking about this without explaining like what the point is? And the point typically is to deliver some energy to a different location. That's what we use our fluid power systems for, right? Hydraulic systems, air systems, water systems, we're either capturing energy from it or we're delivering energy to something that's going to capture the energy. So it's a great way to transfer energy, but we got to kind of figure out like what it is. So let's talk about just, most of us have some understanding or at least some feel for horsepower. Because like our car might be rated at a horsepower, or our lawnmower might be a 2.3 horsepower Toro, you know? All these horsepower things come to us in different forms. So let's just capture what a horsepower is. Horsepower is work over time. So always has a time factor. When you're talking about energy, you're talking about things like watts. Watts is a unit of work over time. So it doesn't just happen in an instant, it happens over time. All right. So 550 foot-pounds per second is a horsepower. And we did literally get a horsepower from a horse. That's how we originally came up with this work concept, right? Because horses did the work for us. So we said, hey, 1 horsepower is going to be an important unit of work for us. If 1 horse can't pull it, then we need 2 horsepower, right? So let's talk about the foot-pound thing, because that is work. If we have feet and pounds together, that is work. In statics, that was torque. It was a foot-pound, right? You take and you apply 1 pound a foot away from something, and you had a foot-pound of rotation. Everyone remember that? Yeah, that was our moment. Moment and torque. So that's this thing right here. If we do it over a second, then it becomes a unit of energy, like a horsepower. Okay. So if you take 1 pound, 1 foot-pound, and move it for 1 second. So 1 pound, move it a foot in a second. That makes sense? You end up with a joule. That's a joule. Same thing, another energy packet that we talk about. So these energy packets are in fluid systems because fluid is not a static thing. Like we don't use fluids in a static form in fluid mechanics. We're going to move it at a velocity, 14 feet per second kind of thing. So when we take these energy packets and you move them, then we get this form of energy that we want to be able to calculate. Okay. So, and then a watt is a joule per second. A joule is a foot-pound in 1 second, right? And then a horsepower and watts, these are all related. They're all equivalent. So kilowatts, that's what you pay your electric bill in. Kilowatts. All right, is these energy packets that are coming to you. Over time, they're not just sitting there. They are delivered to you. They're moving, right?
So is it possible you could calculate that in horsepower?
Absolutely. Yeah, you can calculate your electrical bill in horsepower. You're going to calculate horsepower in a second for me. Because I'm going to have you move these concrete blocks. You'll see them around on the tables. You're going to move them 1 foot in 1 second. So you're going to have to measure a foot, and you can use a pencil on the table for the start point and the end point. And then 1 second, you're going to slide that thing. And what I'd like to know is how much horsepower did that take? We're going to calculate horsepower here. So what do we have to know? We have to know we're moving 1 foot. We have to know our pounds. What does that thing weigh? Does anyone remember? That's great, 6.75. Let's use that. So if we take 6.75 pounds and we move it a foot in a second, is it gonna be equal to a horsepower? 1 horsepower? No, you'd have to move what? 550 pounds. 1 foot in a second. That's how to get to full horsepower. I couldn't find any 550-pound blocks for you. I know Evan wants to do that. But if you push your car, what's your car weigh? Yeah, it weighs a couple tons or a ton and a half. If you push it 1 foot in a second, it's hard to do. You might think it's easy to do, but it's kind of hard to do. It would take 1 horsepower or more horsepower, right? Like 3 horsepower if it was 1,500. That makes sense? So a horse could do it. 3 horses could do it, I guess. Yeah.
It's friction involved.
Oh, friction is big time info. We're just ignoring it. Yeah, and you have a pretty slick surface, actually. But friction is going to take some of this energy and it would add to the amount of horsepower required to move this thing. Absolutely. We are going to consider friction in the fluid systems that we do, but not in the beginning. We're just going to neglect friction. And then we'll do the Moody diagram. Anyone heard of the Moody diagram? You're going to learn to love it. That's sarcasm. Where is it? It is. I just gotta show it to you because it's so fun. Moody diagram. All right, Moody diagram, friction factor for pipes. So when we decide to add friction into the equation, this is the diagram that we're going to work with. But there's things on here that you're already learning, right? Like, look at that, if you can see it. Right? Bottom of the graph, Reynolds number. Over here, relative roughness. Over here, so it's a 3-walled diagram. It's fun, but not yet. All right, let's take 10 minutes and try and figure out the horsepower. And I actually want you to slide it a foot. I want you to feel it. So, ready? Go. One foot in 1 second. If you do it faster, you're doing more horsepower. You do it slower, you're doing less horsepower. After you do it, calculate what you think that horsepower is.
Calculate mean guess?
What?
Mean guess?
No, calculate it.
High school, I a lot of weight.
Yeah, absolutely. Yeah. Yeah, if you bench press 200 pounds, you do 10 reps in 10 seconds, you can calculate that horsepower. Yeah.
I did,
You just gotta know how far you're moving it, right? Yeah,
well, stress.
yeah, yeah. So just measure that length. That's your distance.
Probably not a lot.
It's not a little, like,
As is me.
you can bench 200.
Oh, but my max is 245, so it's not. No, you wanted it.
It's a lot.
It's a lot, but it's not.
It's a lot. £6.75, right? And then how do we get our amount of work done? Work is foot pounds. We multiply by feet. 1 foot. And then how much time did it take? Took 1 second. Right? And then how do we determine how much of a horsepower? Because this is horsepower, right?
By 16.
Yeah, it comes out to be in the unit of horsepower, but we know that a horsepower is 550 of them, and we only have 6.75. So it's a proportion of the 550, right? So if you divide by 550, like if it was 550 over 550, that would be 1 horsepower. If it's 550 and you only have 500, right? Or the other way around, if you only have 500 and 550, then you only have a portion of it. We only have 6.75 over 550. Gives us what?
0.01.
Yep. Not gonna get very far that way, folks. You need a little more horsepower. Kind of get that concept? We had to have time involved. Without time, you just have work.
So horsepower is, so like if you were to use this example so that you feel it, if this was 550 pounds.
Yep.
And you were able to push it.
Yep. 1 foot at a
So
second.
horsepower is like.
It's fairly
decent
significant.
power.
Oh, it is. Yeah. Just
Power
think
of a
about the
horse.
power of a horse. Yeah. I mean, that's kind of contextually wrap your head around it. Yeah. It's interesting though, because when you look at a car, that tell you like, hey, it's 300 horsepower. I'm like, no, it's not. It's 0 horsepower. It's just sitting right here. Like you need to light that thing up for me to see the 300 horsepower, right? Yeah.
You can break amps.
Yep. Absolutely. It's just, it's flow. Amps is flow. So, all right. Let's now talk about our energy in a fluid system. And hopefully we'll kind of get this. The first equation they have in the book is the continuity equation. The continuity equation is basically saying that a fluid in a system, its mass does not change. As long as fluid is not exiting or entering the system, that's important. So this equation works well in closed systems where fluid is not exiting or entering the system, like your hydraulic brake system. Nobody taps into that and adds something. At least you shouldn't tap into that and add something, because now mass is leaving the system, right? So this equation works. Area 1, velocity 1 is going to equal area 2, velocity 2 in a system. Okay, so like if we had a pipe and then that pipe goes down in size and we have station 1 and we have station 2. So we'll work within the system and then we'll also work at the exit of the system too. But this one is a good example for within the system. Fluid's coming in, let's say at 4 inches per second. And I'd like to know how fast it's moving here. Velocity 2. Right? Because is it clearly the same? It's not the same, right? It couldn't be. If the mass stays the same within the system, in other words, the flow stays the same because this is equal to flow, right? Q1 equals Q2. The flow rate can't change. So if there's a flow rate here, the flow rate here is going to have to increase to be the same. I mean, the velocity is going to have to increase. It's going to have to go much faster. So we'll say this is 1 inch in diameter. And we'll say this is a 1/2 inch in diameter. So the continuity equation says, all right, the mass doesn't change, that nothing's being tapped, no fluids entering the system or exiting the system. Q1 has to equal Q2. We can just set the formula up. Area 1 is going to be, I'm going to write it in the pi d squared over 4. So that's area 1. Velocity 1 is 4 inches per second. And those are multiplied by each other. And that's got to equal area 2, velocity 2. Area 2 is pi 0.5 squared over 4. And then velocity 2, which I don't know, and I want to know. What do we get for velocity 2? Anybody else? Yep. So how much did the area reduce? From 1 inch to a ½ inch? Isn't that just half in half, right? So it's not linear, obviously, because the velocity went up from 4 to 16, right? So
Is it quadratic? Does
probably in a circle maybe, but if we can have other shapes. Yeah, I would guess it would be consistently that. Yeah. And again, we're not dealing with friction losses because there is friction losses right here. So this is not conservation of energy. We're not talking energy yet. This is conservation of mass, where the flow rates need to stay the same. So when your pipe size changes, or there's any other changes, the flow rate's going to stay the same, and you can rely on that and then calculate some things. So if we knew velocity 1 and velocity 2, if we knew those differences and we know one of the areas, we could calculate the area of the third. So you're going to need to know 3 things of the 4 variables to run the equation. So sometimes you got to find those 3 things. Like if you're given flow rates, you got to get to velocity, right? So you got to go from flow to velocity, which we've done a few times now. And then just fill in the pieces and calculate the unknown. The key is you got to have steady flow, which we'll talk about quite a bit, meaning the flow is consistent, it's not variable, right? And nothing can exit or enter the system. It can't branch. Doesn't work then, obviously, because the mass branches too. All right. The energy is not the same. We have a higher energy state at 2 than we do at 1. So the available energy is more at station 2 because we have a higher velocity. So when we talk about energy in the system, we're going to use energy head. So the book describes it here. If you're trying to wrap your head around this, how can we do this? They describe it here as head is energy over weight. So when we have energy, foot-pounds, and we divide by weight, we end up with feet. So when we talk about energy in a fluid system, we just talk length for all the energy forms. And if we have the same unit, we can add them. In other words, there's energy due to head, which is the depth of the water. We know there's pressure, there's this weight, and this weight's going to fall, just like you slid the brick. That's work. How do we generate power at Bonneville Dam? We drop water. That's how we do it. We take a weight of water and we drop it 15, 20 feet onto a turbine blade that spins it. That's how we make power. It's called potential energy to kinetic energy. Because when we drop it, when it hits the turbine, it's booking. It's going fast, has a bunch of weight to it. Boom. Okay. But to understand that velocity energy, we talk about it in the unit of length. To talk about the potential energy, this weight up high, it's up a certain height. We talk about it in unit of length. There's also pressure energy. we talk about pressure energy in unit of length. And we do that so we can add the potential energy, the velocity energy, and the pressure energy together. Because if we don't do it, then they all have different units and you just can't add them together. So Bernoulli developed a way to categorize energy in terms of head, which is feet or meters. Each unit of the energy, you can turn it to feet or meters, and then you can add them up and get your total energy. So it's probably the coolest thing that's been done in this field forever, and it was done a long time ago. That was a cool question.
I just always assumed dams, it was the flow of the river that was spinning.
No, when you dam a river, the velocity of that river is pretty much zero. Yep. Now, there's water wheels. There's other ways of doing it with water, right? A water wheel uses the velocity of the river to spin the wheel.
Right.
But not dams. Dams stop the water, hence the fish problem. Stop the water and then drop the water. So,
Have they figured out a way to get fish through?
oh yeah, we have fish ladders. We just have to educate the fish on where the ladder is. So that, that's a hard job. Now and then you see people down there trying to educate the fish, but yeah. And there's good ladders and there's poor ladders, so we're better at it now. So, yeah, anytime you see a dam, you gotta try to identify the fish ladder, because it's usually a very long spillway that's very gradual and it just goes in steps, right? So the Clackamas River has a really great fish ladder. It's like 6 miles long. So because it goes by 2 dams, and then instead of just doing one fish ladder, they said, well, it's gonna build a long one. Well, high school kids found out about it and they float down that thing all the time, even though it's got like screens over it. It's super sketchy, super sketchy. But yeah, the fish can go by 2 dams in that fish ladder if they find it. They usually find it because the exit to the dam is so violent and turbulent that they can't progress up the exit of the dam. So they search around for another way and then they find the fish ladder.
So it's really, it's
Yeah,
intuitive for them to go.
like 2 weeks ago during the salmon run, the fish ladder at Bonneville is phenomenal because there's an area that you can go underground and it's all glass and you can just see cohos, silvers just booking up there. It's super cool. Yeah. But they're all through there now, so now you just see weird fish, eels and things in there. All right, so let's talk about the energy forms and their little equations and how they work. So position head, that's the potential energy. That's just fluid up high. So like if you have a reservoir and then you have an outlet to the reservoir, or if you have a dam and you have an outlet to the dam, the position of the top of the water and the point at which you want information is called position head, potential head. And it's just the energy that's there due to the weight up in the air. And we refer to it as H1 for station 1 and H2 for station 2. So if I had a little picture of a reservoir with an outlet like that, we're talking about H1 here and H2 here, right? H1 is always at the top of an open reservoir. If you're talking about a closed system, then you just have station 1 and station 2, wherever you're doing the analysis. So station 1 might be right after the pump, some pump that's pushing things, right? And then station 2 might be at the end user location, right? And that might be all just horizontal, or maybe it does run up and down the factory floor kind of thing.
And those are elevations.
Those are definitely elevations normally.
And you just add them.
No, you don't add them because they're elevations. So we'll talk about the full formula, but H1 goes on the left side of the formula and H2 goes on the right side of the formula.
Is that an equal sign between H1?
That is an equal sign,
Okay.
because we're going to talk about conservation of energy. Energy in equals energy out. Energy in will be here, energy out will be here. And they've got to equal each other because that's the conservation of energy. And this is the beginning of Bernoulli's. Sometimes the problem will tell you the head right off the bat. the hydraulic head is 42 feet. They've already done H1 minus H2, and they have the difference, because really we just need the elevation change, right, between the two. So you'll get it in different ways. But if you get two, the elevation of H1 is this, the elevation of H2 is this, you put it in just like that. Because what do we do to solve anything here? We just move H2 over and it becomes H1 minus H2. Okay. Velocity head. V squared over 2G. That's our formula for calculating the energy for velocity head.
And G is gravity.
G is gravity. So let's look at the units. Feet, we'll say feet per second. And then 2 is just a constant. And then it is 32.2. Anybody remember the unit?
Second square.
Yep, feet per second squared. Whoops. Got excited. Right? These are squared because that's squared. So just the unit analysis, here, let's just do that. Let's do the unit analysis.
What's the physical meaning of a square second?
Good question. Ask AI. It's got to be some space-time continuum. All right, so what happens here? Feet squared, second squared, feet, second squared. So it's second squared, right? This is in the denominator, this is in the denominator of the denominator, so what happens to it? Goes away. And we have feet squared above, feet below, what do we end up with? Feet. Unit of feet, so be really careful with your units, because in every energy calc, you need to end up with feet. If you're not ending up with feet or meters, you're missing a conversion, you're missing something, okay? So that's how we calculate it. It can be V1 would be here and V2 would be here. So that means the left side of the equation can get V1 squared over 2G. And the right side gets it, V2 squared over 2G. So
Is that a two? 2G,
2G,
okay.
Yep.
I thought it was a Z.
no, 2. So again, this is energy in, this is energy out. A lot of times, some of these will zero out. For example, what's the velocity of the water here at station 1? The top of the reservoir? 0. I mean, the wind might be blowing it around. And it actually might be moving at a very, 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 very small amount. But in a tank, it's not moving at all. It's just sitting there, right? So in our snapshot of time, well, what's the velocity? 0. So that means this one goes to 0. And that's usually how you show it. So when we get to full Bernoulli's, you're not going to do that yet. You're just going to count individual ones for homework. When we get to full Bernoulli's, I want you to write the full equation and then zero out the things you don't need. And often you'll zero out quite a few of them. So the more complicated systems, it'll all be in there. It'll be chaos. But all right. So now we've accounted for the velocity head, the energy due to the velocity. It's here because there's definitely a velocity here. Agreed? That's an open pipe. Yeah.
Just curious, do you know why we're allowed beyond just because the units match up correctly?
Yep.
You know what it means to divide by 2 gravities?
I don't. The derivation of the equation is in the book. It's like 2 pages long.
So it must be-
And then I definitely don't go through it. All I really care about is you can run the equation. But it does go through like the concepts of how they got to this concept of this unit of head, you know, because it's kind of, it's cool because you can collect energies in the same unit and add and subtract them. Like if the velocity energy was some unit like, you know, feet per second squared, and then you have pressure in PSI, like you wouldn't be able to add these things together. But since we can put them all in feet, we can add them and subtract them.
You represent like a ratio.
Yeah, each one would then separate out. I don't know if I'd use ratio, a multiplier, I guess I'd say. Yeah.
Thank you.
Yeah. Pressure head's pretty easy. So when there's pressure in the system, we can account for that energy available, right? If you had a higher pressure, there's more energy available, lower pressure, less energy. You take the pressure and divide by the specific weight. Okay, again, P1 and P2. Right, so they're always associated with the station. P1 over the specific weight, P2 over the specific weight, and we're adding all these things. Energy in here, energy out. If you have an open system, like a reservoir and an open pipe, if this is open, what's the pressure here? Is there any? No, it's free to go. Like it's free to exit. So like the end of your air system, when you have it pulled open and air is just spewing out, there's no pressure there. There's a bunch of velocity. But if you close it, then boom, we have a bunch of pressure, right? When you open it, pressure's gone. So in this system, in a reservoir system, P1 goes away to 0 and P2 goes away to 0. If you close the gate, that's a whole different story. Now the velocity goes away and now we have a bunch of pressure. Okay. And the last one is our friction head, H sub F. So H sub F is complicated and we'll separate that out and do it. It has a kind of a longer formula. It only goes over here though, minus H sub F. It does not go in the energy in calculation. It only takes energy away from us. So this is energy out. We would have this, but we're going to have less due to friction. Again, it'll be in feet. So this will be feet, 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 feet. And we can calculate energy available based on head. Cool. There it is, Bernoulli's in all its form. It actually gets a little bigger, but that's as far as we're taking it. Your homework is just the energy forms. So I think it says things like calculate the, what is the velocity head, the flow in problem 1? So when it says velocity head, that's this equation. All right. So you got to go back to homework 1, look at that. Find the velocity, calculate the velocity head. Pretty simple.
Chapter 4.
Yep, still chapter 4.
So this works for like
5, 6, and 7.
Mercury too, or like some other.
Any fluid, yeah. Yeah, any fluid.
Chapter
Yep.
4, 5, 6, and 7.
Chapter 4. Problems.
5, 6, and 7.
Yeah. So then 6 is pressure head, and then 7 is again velocity head. So this will go pretty quick for you.
Sorry, can you repeat one more time? It was chapter 4, 5, 6, 7, 6, 7.
5, 6, 7, right there. And then we'll work our way into Bernoulli's doing full systems.
Third quiz, right?
I don't think so. I didn't put it on the calendar. Does Evan want one?
No.
Oh, it's the only way to raise your quiz percentage is to take more quizzes. No, I was actually thinking,
I need to know.
I was thinking next week,
Big next week.
so. Here, I'll put it on the calendar, so now you know.
People gotta give us some homework.
Why?
Quiz 2. Friday. All right, that's it. We're done. Nice job.
You need to do, I'm asking a lot right now.